Hello, and welcome to a personal project presentation of mine where I'll be discussing a ball balancing control system I made recently. So in this presentation, I'll introduce my project. I'll overview the system and actually demonstrate it to you live. I'll discuss some experimental results that I acquired, and then I'll discuss the next steps I'm planning and conclusion. So to introduce my project, what made me want to make on my own time a ball balancing control system? It's the classic ball and beam control system. Starting at the bottom here, I took a class in statistics and probability this winter break from MIT OpenCourseWare, so anybody could take it. It's really cool that they have this free. And at the end of it, they showed this reinforcement learning sort of control diagram. And I had known from my aircraft stability and controls classes that I basically that's a fundamental thing to aircraft stability controls is actually making control systems. So I knew the theory really well because I'd studied the math and I knew, all the quaternions and all these like the FFT methods, but I actually didn't have my own control system. I'd made a PID controller in the past for the team, but I didn't really have anything my own that I could really learn from. And then I YouTubed Arduino projects, and okay, so you can see my mouse like that. Okay, great. So YouTubed Arduino projects, and there's so many cool versions of the ball and beam method. There's so much you can do with it, the ball and beam control system. And so lastly, I really kind of knew that I was interested in flight controls. Definitely some of the coolest stuff ever you can do with flight controls and aircraft. And I decided, I want to do this in my own career. So why not learn by doing? So that's what drove me to make the system. So this system's only about 1 month old. About a month ago, so during winter break, I got my sensors and servos and prototyped a really quick system. And I wrote a code up in MATLAB to basically it's just a PID controller. And it was pretty rudimentary, so I improved my my system's like structure. So I made a second prototype, which I'll be showing you today, and wrote the code up in Arduino, which had a faster loop frequency. And then I tuned both controllers sort of individually, depending on what I thought were acceptable results. Then I wrote a algorithm so that you could like basically experimental trials would be automated. And then sort of backwards, I made the Simulink model, and now I'm developing finer, more, better methods to tune my controller through Simulink especially. So right now I'll overview my system, and I'll actually show it to you right here. So, all right there. And let me, over on this screen, I will show you, there we go. All right. So you can see here's the ball and beam. And what I have here is I have it running so that the basic control system will always put the ball back at my set point. And you can see up on your screen, the blue line represents the position of the ball, at least measured by the sensor. And then the red line measures the input of the servo. So you can see I give it a displacement, and now the servo is being controlled to put the ball back in the middle. So I'll go back to my presentation now. All right. So you can see just a quick diagram. I have some system parameters here that I just found from my system, and they're important for the transfer function. But the main thing here is I'm controlling theta to basically reduce R. So R is my state variable, and theta is my control variable. this transfer function here goes from the servo angle uh, to the state, so to the position of the ball, so or the acceleration of the ball. So that'll be really important moving forward. So you can see here it is in the block diagram, but it's a single input, single output system. Um, and this is just my Simulink model with some results that I've gotten from here so far, but I'll go through each block very briefly. So the sensor, of course, has noise. So this block here accounts for the noise. And what I've noticed in this sensor is that the noise is proportional uh, to the distance the ball is away from the sensor. So it seems to follow an exponential curve. So that's something I'm working out here. And if I basically all the filtering methods that I'm using take place in this block. So then with the measured error, so that's R, I have my PID controller, which uses proportional, integral, and derivative terms with gains that I've tuned to basically drive the ramp angle. And what's important about this, I also had to sort of include constraints to the command. So you might have seen in the demonstration that I did that the ramp angle can't go above. I think it's about maybe 10 degrees now, and there's a dead zone for the proportional term. So those are all things that I've been implementing and trying out. And now in my servo model, I have to account for the saturation and time dependency of the response because the servo itself is a PID. It's controlled by a PID controller. And then here again is my my transfer function to go from the ramp angle to the ball acceleration.